Today, I'm going to start with the other three pre-Socratics. We'll see how we do. The other three, remember last time we were talking about the Milesians? The Milesians were physicists. They were interested in what the ultimate stuff of the universe is. And these guys are interested in what the patterns or the laws or the things governing the universe are. And that's going to be Heraclitus, Parmenides, and Pythagoras. I'm imagining that many of you or some of you joined this class because you were hoping there'd be a lot of stuff on politics and ethics. There is going to be ethics, but to the extent we're going to have political discussions, it's going to be limited to what the fundamental premises or assumptions are of some of the prominent political thinkers, namely Marx and Hobbes. They're not primarily political thinkers for me. They are people that have a worldview about where we get our information or where we get our truth or what we believe in. That's what I'm interested in. So as I said on the first day, this is a class mostly in metaphysics, meaning what is real and what is our evidence for what is real. So anyway, we're going to go on with Heraclitus, Parmenides, and Pythagoras today. And so let's just start with Parmenides, I guess. Parmenides was from Italy, and all these guys were taken very seriously by Plato. And by the way, that's why we're studying them, really, because they were all important for Plato. If I had to study them in just by themselves, well, like I said last week, we have only little bits and pieces of what each of these guys said. So it would be just me making up stuff, which is what people usually do when they talk about these guys. And so there's not a lot of substance there for me to speculate on, although they were all very important for Plato, and Plato's very important. So, okay, enough of that. Parmenides believed that nothing ever changed. And the way he thought about this was just logic. He said, if something changes, then it has to become something that doesn't currently exist. But nothing can come out of nothing. Something can't just appear that didn't previously exist. So therefore, nothing changes. At the same time, whatever exists now, if it changed from something previous, that thing doesn't exist anymore. And likewise, things don't cease to exist. So things neither magically appear nor magically disappear. Now, that might seem like thin logic to you, but bear in mind it is exact logic we use in the first law of thermodynamics. So same with Thales, who intuited, I guess that's a word we could use, that there must be some eternal substances that don't leave or don't come and go, and they make up everything. This is the foundation of the periodic table. And Parmenides' insight that in some way there must be something that just is always remaining is the foundation of the first law of thermodynamics, and also E equals mc squared, Einstein's theory, that things change state, but they don't cease to exist. That's pretty much the current thinking. Now, I'm not just to be clear, I'm not trying to credit Thales and Parmenides with some kind of eternal knowledge that they intuited from the universe. I'm just saying they had kind of an intuition about what reality was. Now, along with what he says about change, he says that everything we see is an illusion. So the changes we see in the universe going on all the time, that must be illusory, because if it wasn't, I'd be wrong about things not changing, but things don't change. So whatever change you're seeing must not exist. And I see your brain saying, isn't that Maya from the Hindu tradition? You might think of that. And it is a very interesting thing. And we're going to get to a similar parallel with Heraclitus. But there is no evidence, unfortunately, and this is, believe me, has been, people have tried to track this down. There's no evidence that the ancient Greeks in this period had any communication with Asia, like specifically India and China. There's no evidence for it. I mean, it could have happened, but the Silk Road wasn't available yet. And it could have happened that people traveled from India to Persia and then from Persia to Greece, and somehow these ideas got spread. That could have happened. We can't rule it out, but there is no evidence for it, any connection between the sages of India and China and the sages of Greece. All right, so Parmenides' student was Zeno. Yes, sir. Just go ahead and speak, Brian.
Yeah, so did Parmenides argue about physical things that you could observe, like wood burning and disappearing, or ice melting, or va water vaporizing, this stuff in our immediate sensory awareness?
Okay, well, Heraclitus is going to talk about that, but Parmenides just, it's very mysterious. I mean, it's hard to make sense of, but he seemed to think that if you observe things changing, then this was illusory, that nothing really changed. Whatever reality wasn't changing. Your mind was seeing change where there wasn't any. I know we can't make sense of that. I can't make sense of it, but that's what he said. But Plato took him very seriously, and there's a reason for that, which we will come to. His student was Zeno, and so Zeno's the famous paradox guy, who had the paradox of, like, if you have a turtle and a hare, the hare, and you give the turtle a head start, the hare can never catch up with him, because to get to the turtle, he'd have to go halfway, but by that time the turtle has gone to another spot. And so, okay, that's one of Zeno's paradoxes. So Zeno attempted to prove that Parmenides was correct, that change couldn't occur, and whatever change we saw was some trick of the brain. That's what was going on. All right, so the idea is that permanence is real. And all of the Greeks seem to have been concerned with permanence as opposed to change. They seem to be have the notion that whatever is the most real is something that it doesn't change. And it's, like I say, it's not different from what we believe with the, say, table of the elements, or the first law of thermodynamics. Those are the realest things from which everything else comes. Okay, then Heraclitus is a guy who believed everything changed. So he's the guy that said you can't step in the same river twice. One of his students said you can't even step in the same river once. But the idea is that the river is changing all the time. And he didn't say this, but likewise, you're changing all the time. And so if you step in the river and then you step out, and if you step back in, well, you're a different person. Maybe you're just a little more comfortable with the cold than you were the first time you stepped in. So the instrument that is perceiving the change is also changing. That's a Heraclitean idea that's going to be picked up by Heidegger in the 20th century. These guys, Hegel and Heidegger, were both fond of Heraclitus. And Parmenides, I can't think of anybody that really bore down on Parmenides the way that we see in Hegel and Heidegger. However, Plato thought he was really important, and one of the important Platonic dialogues is called the Parmenides. Anyway, I can't spend a lot of time on these guys because I'd just be making up stuff to say that we're not certain of. That's about the best I could do. Now I want to move on to Pythagoras, and Pythagoras seems to me to be the most important guy since Thales, and maybe the most important guy ever in human thought. And I think on my very best days, I cannot convince anybody of this at my best, because I say this because it took me about 15 years to understand why that was the case. But I'm slow, you guys are going to pick it up much faster, I hope, than I did. But why is he so important? Well, of course, you probably learned in elementary school that Pythagoras figured out that if you have a lyre string and you cut it in half, that you're going to get a note that is the same note but twice as high. It's an octave. And this insight was so profound to him that a cult grew around Pythagoras. Again, he's among all these guys we don't know anything about. He's a murky figure. As a matter of fact, the Pythagorean theorem, he may not have made that up. We just know there was a group called the Pythagoreans, and they were very influential, and Plato was very influenced by them. But they were a cult, and they probably had a secret handshake, and they were vegetarians to a great degree, very strict vegetarians, and they were quite weird too. I have a what they did was they discovered the magic of numbers, but what they did was and this happens a lot in thought, they got a bit overly excited and full of themselves about how important numbers were. I'm afraid maybe that's not a nice thing to say, but they when they had covered this kind of mysterious fact that numbers can represent things in the physical world, they believed they had uncovered a mystical fundamental law of nature through which everything would be revealed. I even have a prayer here that the Pythagoreans said to something they called the Tetractys of the Decad. Let me see if I can find a picture of that, because just bear with me a second here. There we go. Okay, oops. Dang. All right, sorry. This is called the Tetractys of the Decad. And this is it's a triangle, and it had to them mystical powers, because I'm not going to go through the whole intricate way they described all the patterns that are involved in this one thing here. But let me see if I can read their prayer. They say, "Bless us, divine number, thou who generated gods and men. O holy, holy Tetractys, thou that containest the root and source of the eternally flowing creation. For the design number begins with the profound pure unity, till it comes to the holy four. Then it begets the mother of all, the all comprising, all bounding, firstborn, never swerving, never tiring, holy 10, the key holder of all." Yeah. So the Tetractys is let me stop this now. It's they just started to see relationships between numbers that struck them as being very, very profound. And they weren't wrong about this. Let's be fair. They weren't wrong about it, but they were also, no, don't want to use the word primitive. They were also just at the very tip of the spear, or the very baby steps of understanding the world through mathematics. It's not like nobody could count before. There's a book called The Number Sense by Stanislaus Dehaene, The Number Sense, which traces the ability of human beings to use numbers historically and also psychologically. So he has tests that have been run on tests that have been run on animals and babies to determine what they can understand about quantity. And you know the tally sign that we use to, like, a tally sign is like you make 4 vertical lines and then a diagonal line, and that's 5. The reason we do that is because, just like this has been tested on birds and rats, just like birds and rats, we can only perceive numbers up until 4 or so. And then if you put 10 vertical lines on a page, you have to count them to tell how many there are. And so by doing that slash in the tally sign, you can have 10 of those, or you can have 5 of those, and then you can see how many numbers there are. But when you get bigger than about 3 or 4 or 5 numbers, you can't really see visually how many there are. You have to use counting. And so primitive early people understood this, and they started to use marks. And we have, at least 10,000 years ago, we have people using marks to count. And I think it's earlier than that. And interestingly enough, there are people today in tribes, in remote tribes, whose counting system is 1, 2, 3, 4, and a lot. They don't have numbers for 10 and 12 because they don't need to, or in their lives they don't really need to. So this development of numbers is in itself very interesting, and counting had to be used for practical purposes. Now, certainly all the ancient cultures knew how to count. The Chinese, the Hindus, and the Egyptians, they all knew that. And they all knew a bit of geometry. Interestingly, the Greeks, Roman numerals are Roman numerals. They're not Arabic numerals. They're not the ones we use. And the same was true of the Greeks. They used letters. And neither the Greeks nor the Romans had either a 0 or a decimal point, which is pretty interesting. Those were imported, I think, probably in the Middle Ages or the Renaissance from India, the decimal point and the 0. That's pretty amazing. But anyway, the Greeks started thinking about proving things. And last time I mentioned that Thales was the first guy we know that made proofs of geometrical things, geometrical truths. He proved them, and it seems as though people before that time didn't care about it. Now, the Pythagoreans saw numbers and their uses as much more than practical. So I was just talking about how people saw the practical need to have tally signs and to have marks and to count goats or whatever. But the Pythagoreans thought that there was some kind of key to the ultimate structure of the universe that they had uncovered. Now, I used to take a guitar to class and demonstrate the fact that in Pythagoras's theory, there is, I'm going to show you another image here. There is the discovery that a bunch of whole fractions that determine intervals in music that we find pleasing. So here they are. These are the Pythagorean ratios that he discovered. And I used to take a guitar and do this. This is true. If you like, if you have a guitar and it's say the E string on a guitar, let's just say the neck is 24 inches. If you cut it in half to 12 inches, it's going to produce a frequency that's twice as high as the original fundamental. And then these are all the intervals that create a perfect fifth, perfect fourth, and major third and minor third, the foundation, fundamental intervals that we use in all of our music, the Beatles and the Stones and Bach and Mozart. they use these intervals, and they are precise intervals. Like if you take a concert A is 440 cycles per second, or 440 hertz. And if you double that, it's an octave higher. And if you have it, if you double it to 880, it's an octave higher. If you have it to 220, it's an octave lower. And if you use these ratios here, you can create with whole numbers all of the fundamental harmonies that you hear in our music. Now, this is very weird, because that doesn't happen. For instance, colors appear in frequencies too, but they don't have octaves or harmonies the way that music does. It's pleasing to our ear that these whole number fractions, when sounded on an instrument, will be pleasing to us. That is weird. What the ear is an analog instrument, unlike the eye. The eye is not analog. We have three colors in the eye that we receive: the red, green, and blue, and they RGB, and they are blended together to create the colors that we can see. But with the ear, what it is an analog device. And so if you vibrate the guitar at A equals 440, the air vibrates in that same frequency.
I understand. Is there something else I can help with?
Hello?
Go ahead.
I'm not. Is somebody asking me something?
Here's what I found.
You got Siri going here.
Oh, yeah, that was Siri. Oh, Siri is in attendance. How delightful. Anyway, getting back to the ear. The ear is an analog device. So what happens is the guitar string vibrates at 440. The air vibrates at 440. And then your ear vibrates at 440. And somehow that gets sent to the brain, and the brain goes, aha. And then if you create the harmonies per Pythagoras, you get a pleasant sound. Now, that might not strike you as peculiar, but it strikes me as extremely peculiar. Why should this counting system that we developed to count goats or bushels of wheat, when you apply it to music and have correct proportions, or these proportions, it gives a pleasing sensation to our ear? And so Pythagoras thought, and Plato thought, there is something about the universe that is resonating in a way that is coherent to us. It's coherent to our mathematical thinking, and it is in harmony with the structure of the universe. I'm not exaggerating in what they believed and what Plato believed. So they intuited that the universe is in harmony with our brains, as it were. Right? There's stuff out there that we can describe mechanically. And when we do, we see that it has a structure that, as it were, resonates or vibrates with our soul, with our spirit. This is very peculiar. And it led Plato. Most cultures think that they are in harmony with the universe. They do it by various means. They tell stories about how their tribe evolved in accordance with the will of the gods, or whatever. Or if many cultures will dance in order to establish the harmony and the communication between themselves and the cosmos. And so that wasn't new with Pythagoras, but the fact that it could be represented in some kind of abstract form that was invented, like I say, to count goats, that did seem very magical to Pythagoras and his followers. And it still does. And as a matter of fact, we don't know why. This is an essential mystery in philosophy and mathematics. And if you think it's not, I was talking about this on Meredith's list the other day, and this is going to be a major Platonic theme. So I was talking about this. This was, I don't know, a year or two ago. It wasn't the other day. And the theory was advanced by somebody, I think it was Neil Mason. He said that, well, we just gather these numbers from the environment, for we perceive them, and then we learn from that, and we build our mathematical systems based on observations. This is the empiricist view of how mathematics are arrived at. But this is no longer the accepted view, believe it or not. I think the tendency now is to think, it's not now, it's has been for centuries, to think that somehow magically mathematics appears in our minds. And the reason that people think this is that mathematics has rules of its own. If you want to look into this, and I don't suggest you do, because it's just going to make you feel dumb. Well, maybe not. It makes me feel dumb. You can read the Wikipedia article on the philosophy of mathematics. There's two of the main theories are formalism and Platonism. And formalism is the idea, basically, we just make up mathematics like the rules of baseball. And the problem with that is that the rules don't seem to bend to our desires. Like, we just changed the rules of baseball for the extra innings a couple of years ago, but you can't change the rules of mathematics. Another issue is that we can't perceive the laws of mathematics. For example, take a number that is 1 with 100 zeros after it. All right, now take the next number, the same number, except it's 0001. The last digit is 1. Are those two numbers the same distance apart as just 0 and 1? Or when numbers get really, really big like that, do they get closer together or farther apart? Because that's what happens in space and time, according to Einstein. If you go very fast, it affects time. If you have a very big mass, it affects space. Are numbers affected in the same way? And you want to say, of course not. But why do you want to say, of course not? Because mathematics seems to follow rules that aren't discovered in the physical world. It seems to follow rules that are just there. And if you talk to a mathematician, when he discovers a new proof, he will not say he made it up. He'll say it feels like it was there and he discovered it. And I'm just going to give you a couple other examples here, or a couple of examples. This is a famous example of a mathematical, this was discovered by Descartes in like the 17th century. Come on. This over on the right side there, we see a Cartesian oval. Descartes in the 17th century, he's the term Cartesian coordinates. That's because Cartesius is the Latin name for Descartes, René Descartes, who we'll get to. He invented the Cartesian coordinates. In other words, the coordinate system, which is called analytic geometry. So you write an equation, and you can draw the circle, so a waveform or something like that, from your formula. He's the one that discovered or developed that idea that you could do that. Well, one of the curves he wrote was this curve here, this Cartesian oval, it's called. This on the left is the eye of a trilobite. And there's two things about the eye that are very interesting. One is the hexagonal shape of these lenses, and I'm going to talk more about that in a minute. And another is the fact that these lenses, it turns out, have this shape of this Cartesian oval. And the way we found that out, by the way, trilobites have been extinct for 250 million years, so it's unlikely Descartes ever saw one. And the lens of the trilobite's eye had to be discovered with an electron microscope. So I don't think Descartes ever saw that either. But it turns out the lens is described perfectly by, the shape of the lens is described perfectly by Descartes' formula. Maybe that doesn't strike you as peculiar, but some guy who just makes up this mathematical process, then kind of scribbles it and uses it to draw a curve, happens to come across a curve that exactly describes an animal that's been extinct for 250 million years on a minute level that that wasn't even perceptible until the electron microscope was developed. I'm going to show you one other example of this, and then I want to ask a question. The other example is this, the honeycomb problem. I don't know if anybody is familiar with this, but this is the shape of a honeycomb. It's hexagonal. And bees develop this kind of shape for their combs, their honeycombs, about 100 million years ago. Well, it turns out about 25 years ago, in other words, in our lifetime, somebody finally proved that this shape provides the most, most perimeter area. In other words, I'm not sure how to articulate this best. It's the best shape. Okay, you could have these little things be shaped in circles or squares or any other shape. What utilizes the space the best? And it turns out it has the best structure. And it turns out it's hexagonal. But the bees discovered this 100 million years ago.
Yeah, Tony, it uses the least wax to hold.
Exactly. It also uses the least wax. So it's the most efficient shape for the bees. Was that Laurel?
Yes. Yeah.
Okay. Yeah, you know this problem. So but the proof was just recently discovered. So it may not seem odd to you because we're so used to mathematics explaining everything. So it may not seem mystical or strange to you that somebody out of their mind using a completely different, the bees were doing it presumably out of trial and error. So, you know, they didn't have a plan. They didn't have mathematics. So evolution doesn't work in that way. Evolution doesn't try to figure out a plan and then meet the plan. It does stuff. And if one plan is more successful than another, then the plan that's less successful just ceases to exist. That's how evolution works. And somehow it came out with the same result that this guy finally did 25 years ago using mathematical symbols. Okay. So this is what Pythagoras stumbled on, the idea that the universe can be represented by little squiggles that we made up to count goats with. And this will apply to getting probes to Mars and trying to suss out the interior of the sun and how it works. And yet, why would human beings have come up with this? And I'll leave this without going on forever about it. I'll leave this with the question Einstein had about it. He said what he wants to know is whether God could have made the universe using a different mathematics. Is there any mathematics that would create a universe except the one we have? That was something that Einstein said, that's what I want to know. So there you have it. That's about all I'm going to say on this today. Any comments, questions? Nothing.
I would just say, as a failed mathematician, it's not unusual for mathematicians to create structures and explore them and prove things about them that don't have any analog until years and years later when someone suddenly
Yeah.
discovers there's a useful application of this technique.
Yeah, that happens a lot. And it also happens, interestingly, that mathematics can create structures that don't exist. Well, as far as we know, like in 17 dimensions. Laurel, am I correct? Where'd she go?
Well, although again, it turns out that mathematics that was thought not to exist, for example, string theory uses 11, I believe, dimensions. So we have real physicists on here who can correct me, Gerald, others who actually, but
I think that's right.
and so all of the mathematics that that we learn is beyond, it's beyond actual the kind of basic counting, algebra, geometry that you learn, say, up through high school maybe. But at some point, for example, you learn calculus, and then Zeno's paradox, which was mentioned,
Yeah.
turns into the whole idea of taking limits.
Mhm.
And the idea that in fact you can't, we don't care if the tortoise and hare never catch up to each other. In calculus, what you care about is that they get within any specified small amount. And if you can prove that, yeah, it's okay, Milka. If you can prove in the calculus world, what we just want to say is, you tell me how close you want to get, and I'll tell you how long you have to go, and that's fine. And so the whole idea of taking limits is another huge leap. And it's interesting when you teach math to people to see where the barriers are that people have to overcome to understand it. So it takes a while for some people to get the idea of fractions. There are still people, a lot of them, who think that a third is bigger than a half.
You know.
All evidence to the contrary. They think 3 is bigger than 2. They know that, so 1/3 is bigger than a half. And then, people kind of catch on to that, and then you move along and people get stuck in algebra on these problems with rates, the two trains going opposite directions. And calculus is kind of another jump, and proofs in there in geometry are a jump. But eventually you get very, very abstract, as Brian says, some of the very abstract stuff. And then you find, weirdly enough, that it turns out to be useful later. So computers, for example, do all this stuff with matrices, and there's this whole field called group representation theory that takes some pretty abstract algebraic things, turns them into matrices so the computer can do the work. And so there, it's amazing, Tony, to think, and I really appreciate this portion of it, to think how far back and how remarkable it was that Thales and Pythagoras specifically laid a sort of foundation for us to try to make mathematical sense of the world. Anyway, this is way cool. This is way cool.
Yeah. Go ahead.
Yeah, I just wanted to make a comment. It seems to me that if you think about the honeycomb example, it doesn't seem weird to me that nature and natural selection would arrive at the most efficient way of doing something long before a mathematician discovered it or proved it. In other words, it's like natural selection is working out its own mathematics, and it just takes the human mathematician a longer time to be able to come to that than it did for natural selection to get there.
Well, I refer you again to Einstein's. Did God take a look at our mathematics before he told the bees what to do? I mean, I'm not saying, I'm not a religious person. I'm saying, why is the universe created in a way that we can understand with our mathematics, which is something that we made up? It's a system that we created. It's not something you can find lying around in the desert. It's a bunch of squiggles that we made up, and yet the thing, Barry, I think the thing that I had trouble with for so many years, and maybe Laurel didn't, but was realizing we take mathematics so much for granted that it describes the world that we don't see why it's weird that we have this ability to describe the world that apparently comes a priori. We're going to get to that word later, but it seems to come out of our brain. Einstein, again, the two guys who were really puzzled about this were not exactly idiots, Plato and Einstein. And Einstein said, what seems to happen, and he's just analyzing his own mental process. He says that it seems as though there is a pre-established harmony between the mind and the universe that allows me to make these calculations, which later turn out to actually represent the real world. Now, how did that happen? That's the mystery here.
How could it not happen?
Well,
how could you come up with a mathematics that described absolutely nothing that we knew? I mean,
yeah. How could it not happen? It could not happen if our minds did not reflect the universe. That we came up with this system that actually wasn't representative of the universe, or as Einstein put it, could God have created the universe without this mathematics, with some other structure?
But let's go back to the evolution notion. Isn't what our thought kind of just stumbling through, and it discovers things that turn out to be useful ultimately? I mean, how did we get that far? I mean, there's a certain amount of faith in saying, well, I've got my Pythagorean theory, but then to abstract that and expand that out as a worldview, or am I just, as I do my mathematics, kind of stumbling around and finally finding something that fits?
Well, I think that Laurel would tell us that in mathematics, when you finally find it, it seems like it was already there. It was a solution that was waiting to be discovered rather than one you created. And evolution doesn't really work like that. It tries until it finds something that is the best result, not an ideal that you have stumbled on, an ideal structure that you've stumbled on. I just wanted to bring up one other thing about evolution. Remember what I said last time about the fact that the human beings had been around for a couple 100,000 years without any evolutionary force pressing us to discover the Pythagorean theorem. There was no, it's not as though people who understand geometry now are reproducing at a higher rate than the ones that don't. It's not as though you're going to be eliminated from the gene pool if you can't pass a calculus test. So I don't see what evolutionary force there was that produced this mental ability.
No, there are all kinds of evolutionary advantages to being smart, Tony. Come on.
Well, no, that smart is one thing.
Being, just commerce. They were, counting the sheep, whatever, Somebody did it better than someone else. And
I would argue though that all happened after our evolution had reached its present state.
No, not necessarily.
Well, when did people start counting then?
How long have Homo sapiens been around? 100,000, 200,000 years? I don't know.
Right.
Probably counting a couple 100,000 years ago, and the better counters produce more offspring.
Well, does that seem likely? Does that seem likely that human beings reproduced at a higher rate if they could count?
Go to any math department and ask if you really think. I mean, go to a math department, walk around and look at mathematicians and ask yourself if you really think those people are reproducing at a higher rate.
You're talking about commerce and
whether they could reproduce at all.
These things are highly correlated. Bigger brains are better. And bigger brains allow you to do a lot of things, to think more strategically, to get ahead of the moose that's trying to attack you, to think about counting in numbers, to be a better consumer. And I think they're all interrelated, and we can't single out a single mental skill and say it was the one, but bigger cognitive capacity was important.
Well, there's little doubt about that, at least for us. But I think mathematics has a special place in our mental abilities, and it didn't seem to be necessary for a couple of 100,000 years. Not at this level. I mean, what Doug is saying may have been valuable. He says commerce, but commerce doesn't require you to think in 17 dimensions. We didn't need to do that. And so the ability to do that may be an extension, like a pre-adaptation, like feathers were for dinosaurs or was for flight. It's probably something like that, but it isn't clear to me what evolutionary advantage there is to being able to do calculus.
I don't think it's an evolution. I think it's surplus time. In other words, the luxury of not having to focus on day-to-day survival, sort of what do we do to survive, and it's only when you have, I'll call it time on my hands, or somebody else is supporting my activities because for whatever reason I'm more valuable to the tribe as a thinker than as a tiller, that ultimately you're opening the door to, well, what else can I think about? I mean,
well, yes, but you could be producing art. Listen, by the way, I don't have the answer to this. I'm just being obnoxious and answering questions. But
I think you're thinking about this wrong. That's what I'm thinking. You're thinking about the ability to think of strength to understand quantum mechanics. You're thinking of that as one gene or something, and the whole idea of mathematics, being good at math, probably involves
property lines,
thousands of genes. I don't know, and some of those may have related to somebody, 100,000 years ago being able to throw a spear more accurately than some other guy. I don't know,
I think I don't know is what I'm going to hang with myself.
Okay.
I'm not saying you don't know. I'm saying I don't know. That to me, this is a very mysterious development in human consciousness. The ability to do the kind of thing that Laurel does. It seems to me there was no practical value for it. By the time Leibniz was around and invented the calculus, I don't think Leibniz had 10,000 children because of this development. And yet it's very useful to us, but evolution hasn't really progressed since Leibniz's day, I would argue.
So
Let's hear what Doug has to say, because he's been raising his hand patiently.
Yeah, Doug, just barge in here, man.
Oh, okay. It just seemed to me a lot of this started out, or a big development was learning where your property lines were so that your neighbor wouldn't take your property and bash you over the head. So you had to be able to calculate, or somebody had to calculate where the property lines were so that you didn't have as much conflict.
That's a pretty new thing, property lines.
Well, Babylon and Egypt and whatever.
I think, Native Americans didn't have property lines.
Well, this is true.
I don't see again how that contributed to the gene pool.
Oh, no, I'm just saying about developing geometry and things like that.
Oh yeah, well, sure. Paul, just yell, man. Don't be so polite.
Well, all right. I understood string theory as an alternate universe. Laurel, you say there are 10 other universes?
I don't know.
Oh, well, you said something about
Oh, the 17
universe.
the dimensions, that string theory, the 11-dimensional string theory stuff, but I couldn't begin to explain it, not being a physicist at all. I just have a few words
How
memorized.
could someone even think of that?
Well, it turns out to be a solution to Paul. I think string theory. Now, Laurel, please correct me, or anybody that knows what they're talking about. String theory is ever since Einstein and quantum mechanics, there's been a problem with the grand unified theory, which means that it's addressing the problem that the theory of relativity, which is very, very well established by experiment, and the theory of quantum mechanics, which is also very, very well established by experiment, do not talk to each other. They're in conflict. And so ever since this was discovered, Einstein himself, but also everybody since then, has been trying to figure out a theory that reconciles quantum mechanics and relativity, and string theory does that. The only problem with it is it can't be verified empirically.
Okay.
Correct me if I'm wrong there. I think that's the issue.
There's a book about it called Not Even Wrong.
Yeah, well, I would be too stupid to read a book about not even being smart enough to be wrong.
Tony, I'd like to throw on sort of a little side issue. You were talking about why it's very pleasant for these harmonic, notes. And if you look at the ear and the way its sound is received in the cochlea, well, the cochlea is this logarithmic structure which just tapers down in size. So and then if you sample equally along that, the distance between the different neurons along that would be harmonic. And it's kind of a good way for your ear to organize information over such a large range.
Oh.
And it could well be, not that it explains too much, that the pleasantness of harmonic notes relates to the way that your brain is physically organizing the information.
Do you know of any studies along those lines? That's a really interesting theory.
Absolutely not.
Would that apply to animals too? You know, who have the same approximate structure of the ear? Do you know if say Simca, who's wandered off here, but who is quite fond of music, that's why his full name is Simeon Pavarotti, and he actually has fairly strong preferences about music. He has a little baby Einstein toy radio, and he will change the channel if he doesn't like the music, and he distinctly likes some better than others. But I don't think, I haven't noticed anything about harmonics driving it, although he really does prefer Pavarotti to some other singers. So
that's so interesting. Do you take notes on what he prefers, or do you know?
I know that he does not care at all for the William Tell overture.
Oh no!
Channel whenever that comes on, but he leaves it on for Mozart and Beethoven and Bach.
Wow!
You ever tried heavy metal?
And he comes if you put on Pavarotti singing Nessun Dorma, he will come running from anywhere.
Really? So would I. That is very interesting. Paul, have you noticed that you have a similar dogma, unless I'm mistaken?
No. I usually play audiobooks and they have no interest.
None of our other comrades have shown this preference. So Simca is particularly. I have a video of him that his breeder took of him having being about this big, climbed out of the puppy pen and intently watching Pavarotti on an iPad.
I wonder, somebody ought to do research on this. Somebody ought to actually do this. Take, 100 dogs and play a variety of music. People have done it with plants. Why don't they do it with dogs and find out the preferences? Maybe there's something to be uncovered there.
Laurel, I have one of your Simca's relatives, right? Indigo?
That's right.
So I will now have a music experiment.
I'm thinking, because we know that we like those specific combinations, the specific chords or harmonies, Tony, that you mentioned, and even little babies, I think, respond to that. And I think there may have been studies. I don't know. We have some psychology people. I would just guess there have been studies with babies to see if they have preferences on combinations of notes, if they can tell discordant, or what we would say were discordant notes. Tony, do you remember when you first noticed something was discordant and you're like, ah?
No, I don't remember anything like that. I I do think it's that the mystery here for me is the disconnect between squiggles on a page and pleasure to your ear. That's what seems peculiar to me. That little formulas on a page, and then you play them through this box, and it goes, and you light up and say, that's pretty nice. I like that. That just seems odd to me. I know it probably shouldn't seem odd because there's the connection between mathematics and music is long established. It still does seem odd to me. I don't care how long it's been established. It seems peculiar to me. And Bach was a particularly mathematical composer.
So Tony, here's a question for you. Why is it any odder that we figured out how to write down scribbles on a page that capture the magic of the universe, if you will, than that we came up with an alphabet that can capture the way we make sounds in multiple languages? I say we.
Well, a lot of people didn't until 500 years ago. An awful lot of cultures until, I mentioned last time that
Alphabet was probably only invented once, the way it actually, the quote alphabet.
Well, I don't know what you mean by that. I mentioned last time that the Greeks used to use something called linear B, and then the Sumerians had cuneiform, and then the Greek language had those letters that were imported from Phoenicia. So the alphabet's been, and the Egyptians had hieroglyphs. So there've been many attempts to write down some symbolization of human discourse. We assume verbal language, has been around for a couple 100,000 years, but not written language.
I think Laurel's point here is the thing of the alphabet as a way of representing language by the sounds. So each letters give us hints about the sounds, as opposed to a hieroglyph or something like that, which uses symbols to represent ideas rather than just representing the sound itself.
Well, you're above my pay grade here. We need a linguist to sort that out. But yeah, I think that Chinese characters were also kind of pictographs originally that got, and probably they all were, but Laurel, just to answer another part of your question, clearly writing has a practical use right away. I can write down something and tell you to read it when you get to the store. If you can't write things down, then you can't recall them and you can't give them to the next generation. But music is not important. It's just an entertainment. It's something to make you feel good. Yeah, it's not of any practical value, which is another weird thing about humans. We have this whole suite of activities that have no practical value whatsoever. Not some animals do too. Other animals do it, but not like us. We mess around to a degree unseen in the rest of the animal world. Okay, well, look, I have covered and more. You guys were so great today to contribute stuff. I'm going to move along next time to. I might show you some pictures of the ancient Near East, and I have like a picture of a linear B and so forth that I might show you next time. And then I think I want to discuss the sophists just a little bit. And now we're going to start concentrating on the thinkers of Athens with Socrates, and then moving on to Plato. That's the plan for the immediate future. So next time, some pictures and maybe something about the sophists, and then we'll move on to Socrates. And again, I will